Okay. So this is where we left off. So the first thing about oxalic acid to think about is its actual mode of action. Okay. So this is a list I made up of the types of mode of actions that various pesticides can have, how they actually affect the pest. So we're going to go to the next slide here. And we're going to look at, I highlighted in red those for which it's plausible that oxalic acid might utilize that mode of action. So a pesticide can have more than one mode of action for the same pesticide. So right up here, we have acute toxicity. That's if you hit something with that pesticide, the pest dies very quickly from one dose. You do an LD50 lethal dose for 50% of the population right there. And that's clearly oxalic acid has that. If you dribble mites with oxalic acid, they will die very quickly and drop to the bottom. So that's acute toxicity. Chronic toxicity is if you feed something or apply it to a pest over a long period of time, it just slowly wears the pest down and it will die eventually. Chronic toxicity. Then you have cumulative toxicity right here. This is like with fipronil, where they had here in Europe, where they were treating the corn plants with fipronil on the seed, and the beekeepers were saying, oh man, our bees are dying from fipronil, and the pesticide company said, no, 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 we did the LD50, and that dose will not hurt the bees in any way. And they were right. That dose applied one time will not hurt the bees. But if they get that dose for 3 days in a row, their bodies do not degrade it fast enough. Like imidacloprid, 4 hours is degraded in the bee's body. So you can feed a bee imidacloprid, the neonicotinoid, day after day after day, and it degrades it very quickly. Fipronil doesn't do that. You feed it day after day, it just keeps increasing in the dose in their body, and they found out, yeah, it was fipronil toxicity after all. The beekeepers were right. If they go back to the same corn plant, or sunflowers, I should say, day after day, that is cumulative toxicity. So any of those might be happening with oxalic acid. And then the big one, what we're looking at, is residual action. So residual activity. So a pesticide like a pyrethroid, which is a fly insect killer, bingo, you get instant mortality, and then after hours or a day, it's degraded. It's no longer toxic. Really. So a lot of insecticides, a safe one would be one with a short residual activity. So if you spray it, say you're in the almond orchard, you want to kill something, you spray it at dusk when the bees stop flying. By morning, it'll be safe. Okay. On the other hand, the organochlorines, like chloridane, their residual activity is on the range of 50 years. So they were used for treating wood that in contact with the ground to keep termites from eating it. And 50 years later, those termites are still poisonous to termites. So they phased the long residual activity insecticides out. Okay, then there's tissue damage. So if you put oxalic acid on your skin, it's going to eat your skin away. If you were a mite or a bee, it could degrade your cuticle, and you might then die from loss of water, okay, rather than actual toxicity of the toxin. And then the last would be behavior, and that could very well be happening with oxalic acid. Clearly, what happens is on the emponium, the sticky foot pad that the mites hang on the bee with. If they touch oxalic acid, it immediately dissolves into the water of that sticky emponium and burns the cell membranes there and prevents the mite from holding on to the bee, and also probably have water loss from there. Then the last one's a behavioral disruptor. And I'll return to that. Okay, so let that go. Behavioral disruptors may be something that's completely non-toxic, but will prevent the pest from reproducing. So all of these are plausible things that oxalic acid may be doing in the hive with the mice. Okay, I'm going to slow down and talk slower for the benefit of the translators here. We've used oxalic acid between Europe and the United States for well over 30 years, and we are still completely blind as to how it is distributed, what its residual action is, and the mechanisms of it in the hive. Can you believe that? 30-some years, we don't know anything. The only analysis of it for residual action is where they've looked at the oxalate ion and tracked that. But oxalate ion is non-toxic to the mice. It's only the acid that hurts the mice, the free hydronium ions that cause acidity. So really what you need to look at is the number of free hydronium ions, how much acidity it has to understand the residual action. So first, let's calibrate all of our minds here of how much is the theoretical dose that would be used for a 90% high kill. So with the ichthyoxal registration, there's 3 approved application methods. One is the dribble application, one is the spray application, and one is the vapor application. Now, on the label it says how many frames, what size colony or how many frames of bees you put it on, and it tells you a dose. So you can divide the dose by the number of bees and come up with the number of micrograms per bee. Y'all with me on that? Okay, micrograms per bee. Microgram is 1/1,000,000th of a gram. That's a very small point, okay? So for the dribble application, it comes up to be just over 100 micrograms per bee. Theoretical dose. Now, obviously, if you dribble it, not 100% of that goes on to the bees. Some goes on to the woodware, some drops to the bottom board, or some goes on to the wax combs. But theoretically, you're applying 100 micrograms per bee on average, okay? With the spray application, 105 micrograms, same number. And with the vapor application, if you're applying 1 gram per brood chamber, the approved dose, that's 50. But we already know that's inadequate. You really have to have 2 to 3 times that much. So it brings us right back up to that 100 to 150 micrograms per bee. So the bottom line is, on the approved doses, the theoretical amount that you apply to all the bees in the hive is in that roughly 100 micrograms range. Okay, so now we are all calibrated, because I want you to remember that number. It's a really easy number, 100. Okay? A theoretical dose of 100 micrograms per bee delivered to a colony by any application method will kill most of the mites in that colony. Okay? Too much science? Okay, it's going to get worse. So now maybe you have some questions then. Well, how big a dose actually shows up on the bees? Okay, that was a theoretical dose. And the second one is then how long does it last on the bee's body after you apply it? So what Rose and I did this last year is a bunch of titration. Now this is stuff I started working on in 2017, did a lot of work in 2018. Titration is a standard high school chemical technique, okay? You start with it's called acid-base titration. So you use a base to neutralize an amount of acid to see how much acid there was. So you start off with the analyte. The analyte normally is some kind of acid solution. So we make our analyte by taking distilled water and dropping 1 bee that's been treated into that water. That oxalic acid instantaneously dissolves in the water, and you swirl it. Now you have an acidic solution. That's your analyte. And you're going to now try to figure out how much active acid there is in that analyte. So you add an indicator. And in high school, you probably use phenolphthalein. Phenolphthalein is completely clear until it reaches a basic pH about 9, and then it suddenly turns bright pink. So I started off using that. The problem is that I could make it change the pink, and then turn my head, turn it back, and be back to clear. I go, what happened? That water is absorbing carbon dioxide from the air, and about every 15 seconds, if you're down to the microgram level, it'll go a microgram of acid creates from the carbonic acid from absorbing carbon dioxide from the air. That's how precise we're looking at it. You can watch every 15 seconds that water is acidified just from carbon dioxide coming out of the air. So couldn't use phenolphthalein. So I have a good friend who's a world-class chemist, and he suggested some other indicators, coloring solutions that change their color that I could use. And the one we used is bromocresol green, which works at a lower pH, which means a higher acidity, so that carbon dioxide is not affected at all. You need a strong acid like oxalic acid for it to be effective. Okay, then you make up a titration solution. So you dissolve a base, typically sodium hydroxide, which is household lye, drain over, but I use a reagent. And you dissolve a known amount into a liter of water. Now you know exactly how much basic solution there is. And you can drop that basic solution in drop by drop, and you can count how many drops or milliliters that goes in. When the color changes, you say, oh, now I can calculate how much acid there was. Are y'all with me on titration? Okay. we're doing chemistry 101 here. I gotta bring you up to speed. And then once you finally reach, when it changes color, that's called the endpoint, and then you do your calculation. So here's what I came up with. You start out with a test tube, you put 10 milliliters of distilled water in, let it already get carbon dioxide. I took this early. This is straight distilled water before it gets acidified by carbon dioxide. Now we let our distilled water acidify first. We want to start with greenish blue rather than the straight blue. This one's and we've made up all of our solutions, and we check them every day or so to maintain this. The sodium hydroxide titrant remains stable for a very long time. Our calibration solution, where we dissolve oxalic acid into water, after a week, that starts to degrade, so we have to make a fresh one, okay? So we can make sure that we're accurate. Then we drop a bee in. The color, the more acid, the more it will change towards orange. Right now, we know, in this situation with this much water and titrant, if it's got a 100 microgram dose, it's going to be right somewhere between this orange and that orange. So we learned by experience. We drop the bee in, we can tell you pretty close to what it's going to be right off the bat. Now we drip in a known titrant, 1 drop at a time, down to the bees. And you have to hold the test tube straight up and down so this doesn't hit the side. And you count your drops until it gets back to the original color. And now, if you know that your titrant is 1 microgram per drop, it will tell you. And so we mix up 3 different ones, 1 at 1 microgram per drop, 1 at 5 micrograms per drop, and 1 at 10 micrograms per drop. So it's really bright orange. We don't start with the 1 microgram. We drip in the 5 or 10 or 5s until it starts to turn color. And then we take it down to the 1s. Just to show you, we always keep a reference for your starting color. That's your control, so you know what color you're starting with. And for this, I made up a fresh solution of oxalic acid so that it was 10 micrograms per drop. Okay, so that's the known. And I put 10 drops of 10 micrograms per drop of oxalic acid into this tube. So that would be 100 micrograms of oxalic acid. So I know I added exactly 100 micrograms to that tube, and that's our color, that yellow almost to orange color. And then I titrated it back with titrants of 10 micrograms per drop. So theoretically, how many drops should it take to turn the color back? I put in 10 drops of the acid solution and to get to 100 micrograms. So I should take theoretically 10 drops of the titrant to get back to 100 micrograms. If you put in 9 drops, it turns to this, not quite there. If you put in 10 drops, that exactly matches the color. As you go 1 over and put in 11 drops, you overshoot to blue. And you go, wow, that was 1 drop too many. I'll just back off 1, and that's the number I record. So it's a really cool system, highly accurate. And if you're not sure, you put the extra drop in, and if it turns to blue, you go, okay, yeah, I was right on the 1 drop less than that. This is with the 10 microgram drops. You can work it. The 1 microgram is a little, you have to have a trained eye to pick out the tiny color variations. But we routinely do it down to the 1 microgram. We'll put that extra drop in to see if it turns to blue. Okay, the Rose here done this thousands of times here. Okay, so back in 2018, when I had this dialed in, I'd be titrating these, and then I had a visitor a few days later, and they said, oh, what you doing? I said, oh, let me show you. I know this batch of bees was running at 60 micrograms per bee. I'll show you the titration. And I start titrating, and it comes up at 10 micrograms, 15 micrograms. What the heck? I know a few days ago that was at 60 micrograms per bee. I couldn't figure out what was happening. Where the oxalic acid or the acidity? I'm not titrating oxalic acid, I'm titrating oxalic acid equivalents. Okay? Where did that go? So I practice on other insect skin, I practice on shrimp cuticle, I practice on cotton, trying to figure out what in the world was happening. So finally, when Rose came on as a helper last July, I said, okay, we're going to figure this out now. So how rapidly does oxalic acid degrade on a bee? So we took bees from an acid-free colony, and so luckily we have all these breeder queen colonies which have never been treated with anything, so no oxalic acid. So we always have control hives that have no oxalic acid residues in them, and they always test out at 0. Okay, so that's handy for us. So we took some bees from an acid-free hive, froze them to euthanize them, and then dipped them in the morning into an oxalic acid solution, pulled them out, let them drain, and dumped them onto a paper towel to dry. And then we kept them either at room temperature or put some of them in the freezer to see with most chemicals, if you want to look later on for residues, you will put them in the freezer to stabilize the chemicals. So we wanted to see how much that would help. Because I had hundreds of specimens in the freezer that we had taken the year before. Then we went out and we vaporized, or I vaporized a hive also. And when you pull the bees out after that 1 gram vaporization, the bees will have crystals like this on the hairs of their setae, actually, not the hairs of the bee's body. Let's zoom in. So this is a bee right here with that, 70 microgram or so dose per bee right here is what you see on the bee. Okay, so then we went ahead and we took those bees out and we started titrating them afterwards. Now first, for reference, I took some oxalic acid, dissolved it in water, and put it on a plastic cover slip. So no organic matter added to it. And then I also took some oxalic acid, dissolved in glycerin, and some I dissolved in sugar, and put that also on a cover slip. And then we went half an hour, 1 hour, 2 hours, 4 hours, 8 hours, 12 hours, 1 day, 24 hours, then 2, 3, up to 12 days, okay? So we're tracking first, every few hours, then up to 12 days. This is the one of just straight oxalic acid and water on a cover slip. Notice 0 degradation. It's very stable if it doesn't touch any organic matter. Vaporization, it drops off quickly by 12 hours. It drops substantially. By 1 day, you're down to about half of the oxalic acid residues on the bee's body. But if you mix it with glycerin, oxalic glycerin, that's this one, that also degrades rapidly. This is on plastic. Oxalic acid glycerin on plastic. Oxalic acid and sugar on the bees. So these now are all on the bees, and they also all degrade rapidly here. So you can see all of them by 12 days are down to the 1 microgram per bee level. Degrades pretty quickly. So what I realized, if you're going to do this, you can't and analyze. You can't put specimen in the freezer and come back a week later and do it. So I had to throw away all those hundreds of frozen specimens. That you got to be calibrating them, titrating this within minutes of application to start with to see what your starting application residues on the bee's bodies were. How are you doing so far? You up with me?
Yep.
Okay. Okay. So let's move on to live bees now. Now that we know we have to do it right away, we'll move to live bees. But first, I was curious about how it distributed on the bees. So we added a fluorescent tracer to it that would glow under black light, a non-biodegradable fluorescent tracer, which will remain active independent as to whether the oxalic acid degrades or not. And now we can see what happens to that solution on the bees. Is it the bees removing it, or is it simply degradation on live bees? So this is an hour after doing an oxalic acid dribble on the bees. And if you look carefully here, I point to this better. See on this bee's wings, all those glowing green dots, there's a little bit on the thorax, there's 2 little dots right there, just 2, 3 dots on that bee, a little bit on the comb glowing, there's some on the comb right there. So anywhere you see this glowing green, so after an hour, it's not even distribution in any way on the bees. It's little tiny specks. Some bees have more on their bodies than other bees do. We'll be returning to this. So then I built a box to fit Rosa's cell phone camera. Total blackout. We could drop a frame in, have a black light inside, and looked at them. So this is 1 hour again after an oxalic acid dissolved in a water and glycerin solution. And so this bee got a fair amount on its wings right there. That one's got a good dose on there. And then a little bit glow on here. Again, very uneven distribution with the dribble method with either sugar or glycerin on the bees, okay? And then, curious, where does it go to? We noticed is, after a day, there was very little left anywhere in the colony. Like none of the bees and very little on the comb. By 2 days, there was no more glow on the combs at all. Curious about that, where's it going? We mixed up a sugar solution with oxalic acid and just painted it right on, brushed the bees off, painted it right on the comb. So it would look like this. Now, these pictures were taken out in the woods where we had this hive, and to take them, we get down on our hands and knees and pull a black plastic garbage bag over our head to shade it, and then an ultraviolet flashlight, black light flashlight, so it would be glow. So you can see the dried leaves in the background. So this is fresh, how it looks. After 24 hours, that's what it looks like. Almost all are gone. Little tiny specks on a few bees and a few little bits in the comb, but it's all disappeared. That's not degradation, because there's no degradation of the fluorescent pigment. That is actual removal. So the bees are removing that solution from the hive. So where did it go? How would the bees remove it? They don't have scrub brushes. Where do you think it went? 80. Good. Good guess. So what would you do to find out if they ate it?
Look in their stomachs.
You'd look in their stomachs, and that's just what we did. So we took samples of bees off afterwards, after several hours, after a day, and froze them, and then came back. And so we took bees then from an untreated colony. This is under black light. We crushed them on a black surface. There's the crushed bees' bodies, and all this is their guts. Okay, so that's the background color with no fluorescent pigment of what their gut content is like. If they ate it, we would see bright green glowing gut contents. These were treated. No, none in their gut. We crushed 150 bees for combs only 8 hours after application. So 8 hours, if they were eating it, we would see it. Out of the 150, we saw maybe a half dozen that had a little tiny specks on the outsides of their body, but none within their guts. And that's an unanswered question still. We don't know where the heck it went. So what I got to do that sticky board thing underneath to see if they dropped it to the bottom or took it outside. Somewhere that fluorescent tracer has to disappear. We don't know yet, but it's not from them eating it. Once again, the answer that makes perfect common sense that you'd be willing to bet money on turns out to be completely wrong. We're really used to that happening with bee research. Okay, so now we're ready to get serious here. Let's apply it to full colonies, and let's compare some different application methods of oxalic acid. Oh, I'm sorry. No, first, at this point, we were curious. Okay, so we know the extended release oxalic acid. Still, the sponges still look moist from the reason for the glycerin, okay, if you have dry skin, no sweat, and you take oxalic acid crystals and sprinkle them all over, nothing will happen. You put a drop of water on there, or sweat, that then allows the acid to dissociate and makes it acidic, and those hydronium ions will eat your stomach. Okay? Until there's water present, oxalic acid is harmless. That's why vaporized oxalic acid on the bee's body is harmless unless they get wet. Glycerin is a humectant, which means it absorbs moisture out of the air, especially at the humidity level within the cluster, that 60%, 40 to 70% humidity level. Our glycerin rapidly absorbs moisture. So we have the 1-to-1 formulation, which is super saturated, and the sponges are covered with oxalic acid crystals and feel kind of dry. You put them inside a hive, and within an hour, they look moist and they have dissolved. And now they're active. So with the extended release oxalic acid, when we check back in the hive, as long as it looks moist on the top of the sponge, that means it's still active. And what we do is a very scientific test. We take our finger, touch it, and taste it. If it tastes like strong acid, then we know it's active with acid, okay? So we were curious, well, how much, let's answer that question. Does the acidity build up over time with the extended release? So we had a couple of colonies in a yard that sponges had been in for 73 days. So let's go out there and test them. So here's the colony. These sponges still look moist. They still tasted of acid to me. So we know that these bees have been continuously exposed in warm and hot weather during the summer for 73 days straight. Let's see if the residues, if we've acidified the hive or not. So we set up our titration tubes. And we looked for an average because we already saw it's not going to be even on these. So we dropped 3 bees into each tube first, and then we went to the hive next door to it, which was an untreated colony, and you can see there's no color change at all when we dropped 3 bees in. So look at the color change. We always have a reference tube. Here's the color change. And when we titrated these out, it was an average of about 2 to 3 micrograms per bee. So after 73 days, you have that 2 to 3 micrograms per bee. It does not build up. It just keeps that low level in that colony. So this made us really curious now about what happens with different application methods. Firstly, you might want to visualize how much a microgram of oxalic acid is. So I scooped up a little bit of oxalic acid in a scoop, and I tried to get the smallest particle I could separate out. This is the end of a chopstick right here, and I dropped it into water, and pretty good color change from that little tiny drop. And that titrates out to about 65 micrograms of oxalic acid from that speck. So a speck that size, 65 micrograms. If the bees only got 2 to 3 micrograms on it, it's going to be a really tiny speck of oxalic acid, right? Okay, so now we get serious. We set up 16 colonies, and they all had, at that point we didn't have very many. My sons had already treated all the rest of our operations, 1,000-some colonies, with extended release. So we had to scrounge colonies from previous formic acid experiments. And by the way, the residues of those formic paths, long after there's no more odor, they are acidic as heck still. And so there was, some of these started with a tiny bit of oxalic acid acidity in them already. And then we said, let's just track this for 2 months straight and see what happens. So we did one colony got vapor, 3 of them got 3 different dribbles, either with sugar, with glycerin, or with propylene glycol, another food-grade humectant on it. 7 of them got sponges applied different ways, either between the boxes with 1-to-1 ratio, with the 1-to-2 ratio, with propylene glycol, and then with citric acid instead of oxalic acid, with sodium bisulfate, which is a food-grade acid, and then the New Zealand, one with no glycerin, and then the New Zealand strips at 3 different ratios of oxalic acid to glycerin, and then 2 half shop towels, and then a control colony. We want to compare all these different treatments for residual action, or for immediate action and residual. And then each hive, I took a brood frame from the middle of the upper box, marked it with green, and labeled it for what the hive number was, so we wouldn't mess up. And we would Rose would prep up 10 test tubes right here, and I would put samples. And we decided to go for averages, or I decided to go for averages, and I put 5 bees in each test tube to come up with an average. In retrospect, now what I'm doing single bees. I'll show you later on. But for this trial, we did 5 bees in each one, so we got averages there. I would take 5 bees, 2 samples of 5 bees from this side of the comb and 2 samples from the other. So we essentially always went to the same comb in the center of every colony and took bees from that comb so we had consistency. And then we would titrate them. And these starting off with a fair amount of oxalic acid on them. So the first, initially, so that we could titrate them immediately after treating, built a chair with a table for Rose, and she sat right next to the beehives, so I could just hand her the specimen and she could titrate immediately. And then I felt sorry for her after that because it was a heat wave. The temperature was up around 37 degrees or so. And so I moved her into the lab next door, and so she had a swamp cooler air conditioner on her, and also fluorescent light inside. So now she was set up so I could take the samples and bring them to her. And then days where I was away, she'd do it by herself. So I thank her a lot. And she'd have the recording data here on her lap right here. And lots of data. This is just one page of it right here for us to then analyze. And here's the overall results. Now we're going to tease these apart in a minute, but right now just to show you the overall. Okay, so all these graphs, I did up to 30 micrograms. So that every graph has the same scale on the y-axis, so you can compare them. And what we saw is with the vapors and the dribbles, there was a spike on the first day. So this would be at, that's 1 hour after, no, I'm sorry. This is 1 day, 3 days, 5 days, and this is intermediate ones. I'm going to about 4 hours or something like that before the first day, just to see what the initial spike was. So you can see with the dribbles and vapors, you got a pretty good spike. And a lower one with some of the other putting in the sponges, a bit of a spike. Not really high, we're like getting up here to maybe 15 micrograms per bee average. And then it drops down, and then you reapply the vapors and the dribbles right here, but at a lower dose of the vapor. And then we reapplied the New Zealand strips right here, and we went to 60 days. Okay, so let's take at this point now, we have taken the blindfold off. We're going to now look into the heart of these colonies and see what happens with the oxalic acid residues over time. Okay? Okay, so first with the vaporization. First with the 3 grams per brood chamber, and then secondly the 1.5 grams. A few of the bees got hit pretty hard initially, but even immediately you had about 20 micrograms per bee. Though the theoretical would have been for this one 150 micrograms per bee. The actual was about 20. And surprisingly, it didn't make a whole lot of difference if you took the bee from the outside of the cluster or the inside of the cluster. It was pretty consistent on the bees. And then we also did dribbles at the same time. So now I'll show you that this is just for the vapor and the dribbles right here. So big, tall for both of them. They all drop down just about at the same rate right here. The reapplication, they go back up again, and this time we only vaporized with 1/3 that we did there, and we, of course, got a lower dose, showing why that 1 gram per brood chamber is inadequate. You don't, even your initial dose is not high enough to get good kill. We're going to come back to that later on. Okay, so and then it slowly tapers off over time. I didn't know why it tended to go up on this last one, 60 days. So I put in, we had 2 rainfall events. I was curious whether the rainfall had anything to do with it. It looks like, in retrospect, no, but I did add that there. Okay, so we had 7 different sponge applications, and here they are. Notice we don't get that great big spike with the sponge applications. It actually takes, you don't really, until a day afterwards, it starts to reach its peak right there, and then drops down and stays fairly low. And again, huge, even these are, each one of these data points is an average of 15 bees. And despite that, look at just the variation. This shows you how much variation there is the distribution there. This is an interesting one. This is a dry sponge right here with no glycerin. And yet, the amount of acidity was fairly consistent in there. So I go, wow, that's interesting. Do we even need to put glycerin in? So I set up 2 hives with high varroa levels and with the dry sponges in there with the acid and tracked them for a varroa kill. And they did not increase the mite drop on the sticky boards, and they did not drop it by the detergent wash. So apparently the glycerin needs to be present in order to activate that oxalic acid to make it kill the mice. Just having it in the hive dry didn't do much. The citric acid had a very nice spike right here, so perhaps we could use citric acid just as well as we use oxalic acid. And the sodium bisulfite is this red right here also looks pretty good. That's another food grade acid used in lots of food processing. So there's alternative acids that we could possibly use. And here's the New Zealand chipboard strips. Manufacturer in New Zealand was gracious enough to send me a bunch of these. They're already pre-cut that we could then apply with the New Zealand with 3 different ratios. And then also the shop towels. So, well, here's the shop towels. We got a nice, and we applied them 1 day later. They had a nice big spike at first and then dropped down here. The rest of the New Zealand strips, it didn't make a whole lot of difference what the ratio of oxalic acid to glycerin was, which really surprised me. I'm going to break that down in a second. But these actually were pretty similar to the sponge applications. these were 6 strips per double deep root chamber. So instead of the 2 sponge strips, this is 6 individual strips, 3 in each root chamber we put in. Now I broke it down here with the 1 to 1 or the 1 to 1.5 formulations in gray, and the 1 to 2 or the 1 to 2.5 high glycerin formulations in red, just to see how much difference the glycerin, ratio of glycerin made. And as you can see, it's these are the gray ones, they could be low or high. It didn't seem to make much difference what the ratio was of the glycerin to oxalic acid. That kind of surprised me, because in my incubator trials, the high glycerin we get on the bees really couldn't kill the bees really easily, because it transfers the acid to the bees' bodies so quickly. But in the hive, that does not seem necessary to be the case. That's going back to that question that you had earlier. So this is, now we're unblinded to your question, okay?
A new one.
Yes, there's always a new question. Always. Okay. Now here's something to think about, this extended release. How many mice are emerging from the brood every day? So I did calculations, and of the total mite population in a colony in full brood rearing, you've got about 7% of the mites in the hive emerging every day. So every day, about 7% of the total mite population is coming out and being exposed to those low acid residues in the hive. Okay, we're talking just less than 5 micrograms per bee. What you see, this is from a study by the HiveBase on the amount of, after extended release oxalic acid with the aluin cap formulation. Aluin cap is the Argentine formulation, named after the town of Aluin in Argentina, and CAP is the Coordinated Action Project by the beekeepers. And so they work for the benefit of the beekeepers to come up with new methods for keeping hives healthy, and they named the strips Aluin cap just after the name of their organization. So that's where that name comes from. And what he showed is, about day 2, when we already saw the spike in the oxalic levels, you get a pretty good, this is how many mites are falling on the sticky boards per day. So initially, you obviously have an acute toxicity of the mites dropping down. And then that starts to slow down after a few days. It goes for about a month. And my data also, I'm not showing today, same thing. For about a month, we see elevated mite drop on the sticky boards. I'm going to return to that in a little bit. And then very low drop after, we show it after about 30 days. Then it stabilizes to a very low drop. Despite the fact that the efficacy as measured by mite wash doesn't show much efficacy by 30 days. You have to go to 60 to 70 days before you start seeing your mite infestation rate start to drop. I know. For the first month, if you're doing mite washes and you put it on, despite that big drop, your mite wash count will go up for the first month. It actually increases rather than decreases. Totally contrary to what we would expect, right? You'd expect that if you're having a bunch of mites drop on the sticky boards, that the mite infestation rate will go down in the adult bees. It goes up for about a month. Okay? We'll talk about that in a little while. Okay. So I did a simple graph, just plotting, because now with my, my modeling, it's really easy for me to say, well, once you kill, every day, you killed 0 mites. Okay, that would be the growth rate of the mites, right? If you're starting with at 1, it would go up to 2 times the amount within a month. If we were killing 5% of the mites a day, that would flatten out. You don't have to kill a whole lot of mites because you have those 7% emerging each day. If you're killing 5% of them, you end grow population growth. If you're killing 10% a day, it's going to go down fairly slowly. If you're killing a quarter of the mites, this is just of the mites on the adult bees, not the mites in the brood. Then after about a month, you would have taken it down. What we see, it actually takes about 2 months. Anyway, this gives you an idea. You don't have to kill a whole bunch of the mites if you're killing some every day. You all still with me? Okay. Are you guys excited about this as I am? This is pretty amazing stuff to figure out. I get goosebumps showing this. Okay, so how does this work at such low residue levels? Okay, so I did an oxalic acid dribble, and I took one bee in each sample. I also went out to the hive next door and did test. I always want to test the untreated control bees, no color change on them. But these guys right here, you can see the variation. So this is probably around maybe 100 micrograms on that bee, and that's maybe 5 micrograms on that bee right there. Okay, so big range. And this, I see this every time. Just you take 10 individual bees, so you're not taking any averages. There's just this huge variation. So now we have a big question here. How much actual oxalic acid on a bee's body does it take to kill a mite? So I did a literature search, and there are two researchers in Italy that have done incredible work over the years. Milani and Nadetti. And I've never met either of them, but they are fantastic researchers, okay? And Milani, in 2001, did a study, and he used what's called a Potter spray tower. And that's a device used for testing on pesticides. It's a chamber with a sprayer, fancy sprayer at the top. You take petri dishes or glass dishes, you put them on the platform down below, you calibrate it, and you do a spray, and it puts an even mist of that pesticide over the whole lower surface. And then you can weigh your glass dishes before and after down to the microgram, and you know exactly how many micrograms of that pesticide was applied. And he applied oxalic acid dissolved either in water or dissolved in glycerin. And now he could quantify that. And then he would take a live mite and drop it into that glass dish and let it walk around for 1 hour, pull it out and put it on a healthy bee pupa, and let it feed on that pupa, and then check back after 24 hours and 48 hours to see whether that mite was still alive. Okay, y'all with me on this? Yep. So he knows exactly what the exposure per square centimeter of surface area was. So now, here is the surface density of oxalic acid in micrograms per centimeter square. Back to micrograms, okay? That means I can compare it because I got microgram data, right? The only thing I need to find out now is what? To compare it. We know micrograms per centimeter squared, the surface area of the bee, exactly. And what he found was, this is your percent mortality. That's 100% mortality there. I don't know why you did these percentages. If you put it on with 10 micrograms per centimeter squared, you're going to kill virtually 100% of the bees by 48 hours. If it was at 1/10 of that, at 1 microgram per centimeter square, you're going to kill about 45% of the bees by 48 hours. So, I searched the literature again. Did anybody ever calculate the surface area of a bee? And sure enough, somebody used computerized tomography and calculated it. The body alone, the body with the wings. So I included the wings, but it's both surfaces of the wings. I probably should have only included the upper surface of the wings. So I'm underestimating the toxicity here. But a bee is about 3 1/4 square centimeters in total surface area of all parts of its body. Okay? Now I can calculate out how many micrograms per bee should result in 100% mortality. It works out, if I titrate a bee at 32 micrograms, so you've already seen these results, that would be like the initial spike, you would expect to kill close to 100% of the mites within 48 hours that walk over that bee. If you're down to the 3 to 4 microgram level that we see with extended release, you're still killing 45% of the mice that spend an hour walking on the average bee in the hive. Isn't that cool that we can now calculate this out and come up with expected mortality for a mite walking on the average bee? Except we don't know how much the mites move from bee to bee. So back to look for the literature review, and luckily, okay, we'll come back. We'll come back to that question. So we're going to compare the acidities of either 1 or 3 micrograms vaporized. I did take this bee right here, which obviously got hit hard. And that titrated out to 1,100 micrograms. That was a very large dose there, and that bee does not handle that kind of dose right there. Okay, so now what I did is I did 2 things. I vaporized them and I dribbled them during the summer with a loose cluster and during the winter with a tight cluster. See if that made a difference. So my summertime averages are these little orange squares, and the wintertime averages was more of that. Those are averages. In wintertime, per bee, each black dot is 1 out of 10 bees. So all the black dots add up to 10, but many of them came up with the same number of micrograms, so you see less than. But some of these you're going to see a whole bunch of dots. I used pretty much pick out all 10 bees there. And then I put a line here for that 30 microgram levels, which we'd expect to kill 100% of the mites, and the 3 microgram level, which we would expect to kill maybe 40% of the mites. So somewhere in between these two lines, we should be seeing substantial mite kill, and up above this line, we would expect to see acute mite drop right away. You with me on this graph?
Yeah.
Yeah? Want to see some heads on? Okay, good. You guys are doing really good. This is a lot of fairly scientific information right here. Okay, so notice that, to my surprise, the summer application with the loose cluster, after this vaporization, this is the high dose, 2 grams. This is low dose, 2 grams per double brood chamber. The summer was actually lower, average was lower than the winter. This is the dotted line is the average of all these dots right here. So I put the raw data of the individual bees to show you the range, and then the dotted black line is the averages. So our average at that 1 gram per brood chamber vaporization is not very impressive, which is why we're not getting very good mite kill in the summer with that kind of vaporization. This is, and this is hours application. Half an hour, hour and a half, 2.5 hours, 8.5 hours, 12 hours, 24 hours, and then by every 12 hours up to 4 days. Which, since I told you this is winter data there, if you're doing it 12 hours apart, what does that mean as far as taking your samples? You're taking the morning one in the snow before the sun comes up, and your evening one in the 12 hours later in the snow after the sun goes down. Not much fun. Oh, but I'll tell you something else. I don't have this slide. It's maybe after the time. One thing that bothered Rose and me all through the summer is every now and then, one of the bees in a sample would turn it, instead of turning it to the orange, would make it bright blue. We couldn't figure out what would make it turn to more basic, not to basic, but less acid. And one of the things, I washed my hands one day in our well water, which was out, I had some calcium in it, calcium carbonate. Oh, it must be my hands, I must have touched something, and I'm rinsing off my forceps, my soft forceps, to avoid contamination, and it just kept happening. But one of those mornings when I went out, it was raining just above freezing, and I have to open up these colonies and take out these samples, and a whole bunch of the samples were blue. I go, oh man, was it due to the rain? Okay, so I looked at that and it didn't make it work for rain. I said, what other variable occurred? Come on, think about it. What other variable would happen if I was out there before dawn on a cold day, opening a hive and taking samples? What would I have noticed?
Moisture.
I don't wear protective gear. What would I have noticed? You open a hive up in the dark, in the rain, before dawn, with no gear, what would I notice? The bees were stinging the snot out of my hands. They don't like me disturbed then. I go, wow, could it have something to do with them stinging? So I took some bees and exposed them to get them to put the stinger out and drop them in, and sure enough, they turned blue. So I go, wow, now is it the pheromones? Is it the sting gland? Is it the tissue around the stinger? So I started narrowing down with a whole bunch of bees, bunch of stings, my fingers doing this. And I got photographs of the tiny micro droplet on the tip of the bee stinger. And I have the solution, the blue solution, and I'm touching it, and you can see it turn to more blue right where that micro droplet hits it. So even though bee venom is slightly acid, it's less acid than the carbonic acid from the distilled water, and takes it slightly towards neutral, and apparently has very strong buffering capacity. Buffering capacity is when something takes a pH and holds it at a certain level. A micro drop of bee venom will buffer that 10 milliliters of water and take care of all the acidity due to the carbon dioxide and make it turn blue. So we finally figured out why we got the occasional ones So the trick is you have to use very gentle forceps and be really gentle with the bees when you put it in. If they're stinging and putting a drop of venom out, it turns blue. Okay. Okay, so now this one, I put in 3 times the allowable dose. 6 grams of oxalic acid altogether for a double brood chamber, okay? Look at the difference. Here's a bee with 130 micrograms. Here's one just under 100 micrograms. A lot more in this high range than we saw at the allowed dose of oxalic acid. And both in the summertime and the wintertime, reversed a lot, up here. But look at how long now we have these high levels up in this range. So clearly shows you why you have better efficacy if you're vaporizing with the higher amount of oxalic acid. Puts in perspective to what we know, these red dotted lines, of what it's going to take actually to be killing mites. Okay, so now let's compare it to a dribble. Now instead of 2 different doses, I applied to 2 side-by-side hives, strong clusters, side by side, the same dribble. And you see, they're similar, but one hive has slightly higher levels than the other, not a whole lot. And compared to back here to the, you see how we're getting down here by 24 hours? We're pretty low with the vaporizations. With the dribbles, we were still above there up to like 72 hours, and this one flew up to 96 hours, 4 days. We're well above what you see with a vaporization. So that's why you get a better efficacy with the dribble than you do with the vaporization. It holds it up there for longer. Are we all learning something here? Isn't this cool? After all these years of using oxalic acid and not knowing what was happening in the hive, now we have our eyes on this. I already published this, and I expect researchers to hop on this and just start all learning and improving oxalic acid application methods. So back to how much the mice move around. Well, Jack Ramos in 2022 actually tracked that, and what he found was over 15 days, some mice switched their host from one bee to another up to 15 times. So that means every day that mite on average was moving to a different bee. Some, though, only were switched once during that period of time. So that's why we're not seeing, with that 45% kill, we're not seeing all the mites dying right away, because some don't move from bee to bee. So lucky mites never get on a bee with a high dose of oxalic acid in their bodies, and the unlucky ones find one of those 100 microgram bees, and they hit that spot of oxalic acid, and they're going to be gone. So that's how this extended release is working with on these bees. And then I did modeling to see where I calculated out what the expected mite fall and repeated vaporizations, and yeah, it fits the field data very, very closely, okay? The one that doesn't fit, though, is this here. This would be for an extended release, assuming that we're going to get 5% kill the first day, 70% kill the second day, then dropping from 40 down and holding at 10% kill per day. What this shows is we would expect our mite wash count at half cup bees to drop and slowly go down. But I already told you that's not what we see. It goes up for the first 30 days. So something else is happening. Put your thinking caps on. I'm going to ask you a question. What plausible explanatory hypothesis do you come up with that would explain why the mite wash count on the adult bees would go up for a month, even though you're killing more mites? What would cause it to go up for the first month? Think about it. Any educated guesses? Let's go back to behavioral disruptors. My guess is that something is affecting the behavior of those mites. Let's do an example. Tracheal mite. When tracheal mite invaded the United States, it was a disaster that moved across the United States from Florida to California. We saw it coming. We go, oh my God, when's going to hit California? It hit California, and it killed 70% of the hives of bees, managed hives of bees in California. Wiped us all out. 70% of our hives, bam, killed by tracheal mite. We were trying all kinds of things, menthol and amitraz and everything else, trying to save our bees. So the Tucson lab, USDA lab, was taking older bees that were having mites come out of their spiracles. I'm sorry, older bees and young mites were coming out of their spiracles and questing, looking for a suitable host bee to invade. Because as the bees die, the mites have to come out and invade a younger bee. And what they had determined was, just like a tick, when it comes out, it climbs up on a blade of grass, puts its front legs up, and just waits. That's called questing behavior. And it waits for the smell of butyric acid or warmth, which means a mammal walking by, and then it jumps. The varroa mite quests for the odor of the fifth instar larvae, putting off that time to cat me over pheromone. That tells the mite that's questing, that's the time to invade, hop off the nursery and go into that larva, okay? They found out that the tracheomites quest for a particular odor, the hydrocarbon odor of a newly emerged worker bee. Because their setae, their hairs around the spiracles, have not yet hardened, and the mite can squeeze into the spiracle and infect a young emerged bee. Okay? One day, so they had this standard technique for getting young bees infested by tracheomites, by putting young bees and old infested bees together in a tub and exposing them for a few hours, and they could pick out the young bees and knew that they would be freshly infested. One day, none of them got infested. A few days later, when they went back to dissect them, they go, wow, none of these bees got infested. What happened? And this is an important lesson for anybody doing bee research, any research. You keep your experimental log with every detail, whether you think that detail is important or not. And they saw that there was a little detail that happened on that day. When you put bees, so I have a background in insect culture. If you want to keep insects in a glass or a plastic container without them crawling out, you take Vaseline and rub with your finger around the inside of the rim of the container. When insects climb up the side of the container, you hit that Vaseline, they can't climb out. So if you want to keep a bunch of bees into a tub, you put a little bit of Vaseline on the top of it. When they look back at the lab notes, that day they had run out of Vaseline. And they used Crisco vegetable shortening instead. And on that day, no mites, no bees got infested by a mite. So they did some more research. They found, wow, simply putting Crisco vegetable shortening in a colony disrupts the olfactory cue for those questing mites, and they were unable to identify a young host bee to climb into. Totally non-toxic, but it was a behavioral disruptor. And we all switched over to putting Crisco sugar patties into our eyes, and that kept them from dying from the tracheomite. Nothing toxic about it in any way. You didn't kill a single mite, but you simply kept them from reproducing. Okay? So I'm wondering, what? What's the question I asked you guys a minute ago? Why would the mite count go up on the adult bees after you put oxalate in there? What if you are messing with their olfaction so they can't identify a larva of the right age to enter? They would just hang out on those adult bees and eventually die of old age without ever infesting a new larva. And I'm wondering if that's what's happening. So I built a little test chamber for an assay, behavioral assay. And I took bees from a non-acidified colony, took a sample of bees out, make sure they were homogenized, divided them into two groups, put them in two different cups. In one cup, I sprayed it with oxalic acid and glycerin, a light bit, put them in the incubator overnight, and then the next day, put them in here, put the oxalic-treated bees and oxalic and glycerin in here, and the untreated bees in there. And then I went to a high mite colony, used powdered sugar dusting to get live mites off, washed them off, and then dropped 40 mites through the funnel in between to see if they had a preference in which way they wanted to walk. And the answer is a very strong preference. The only variable difference was that these bees had been treated with oxalic acid and glycerin. Now, one thing you should know about oxalic and glycerin, it immediately forms esters, oxalic esters. Esters are, most of the smells of fruits and many flowers are esters. It's a combination of an organic acid and alcohol or a sugar. And the glycerin does that also. So we don't smell that. That doesn't mean that the mice don't smell that. So my question is that oxalic acid and glycerin, which are obviously reacting because you see the acidity disappear, are they creating an ester that disrupts the mice old-fashioned? So I was really excited. I talked to some other friends, and they said, well, Randy, you should jump the plastic, because the plastic might, kill it off or might absorb that. You should build one out of aluminum instead, so there's no, odor, no outgassing from the plastic, or no absorption. So I did. I built a really nice, I want a picture of it, aluminum device. And these are little stainless steel grates from a animal comb. So I'm already got it all set up, my fancy new device, and I had my 2 high mite hives ready to go, and I went out, and they both died from the mites. And that was this autumn, it was like November, and we had no more high mite colonies in the operation. So I've been on the edge of my seat since then, waiting to find a high mite colony, so I get enough live mice to continue this bioassay, because I've only done it once. You can't learn anything from the end of one. I need to see if it's consistent. If I can repeat this season, when we finally find a high mite colony, I'm hoping when we come back from almond pollination, we're going to have, when we start mite washing, we'll find one high mite colony. That's the thing. I'll do anything for a bunch of live mites right now to test this assay out. If we find, yes, there is a clear olfactory preference in one way or the other due to oxalic acid and glycerin on those bees, we're opening a whole new way of mite control, perhaps even maybe non-toxic. So we'll see. Okay, I'm going to wrap this up now. Here's the point. Researchers are just wanting money thrown at them to develop the next fancy miticide, screening all the possible toxic chemicals to test them out and everything. My point is, we don't need any breakthroughs. We don't need any high tech. These right here work just fine. 21 years, that's all we've used, okay? We just need to learn how to properly apply them. That's why this research I'm doing, it will give us the window. Now instead of taking months to do an assay in the field of trying different treatments and seeing what the mite reduction is, we can go in the next day and do titration and go, oh wow, that's not going to work. There's no acid on the bee's body. We can now accelerate our experimentation of potential treatments, okay? The problem is, we have too few registered products right now. We can't legally change the label on aphioxyl. You're not allowed to increase the dose on the vaporization. With my time-wall treatment on the homozone, you can't legally do that because it's not a registered formulated product sold by a chemical company. We are an orphan industry. We are a beekeeping industry. It's not worth it to the chemical companies to pay. For them, it's $800,000 in the U.S. just to get through to the first step to the door with the EPA to register a new product if you're a large chemical company. They charge less for small companies. They're not going to recoup their investment with something that beekeepers can buy off the shelf. They know the beekeepers, if they come up with an oxalic acid formulated product, beekeepers are going to go, oh yeah, I can go to the hardware store, buy wood bleach and use that. We've already trained the chemical companies that if we can buy it off the shelf, you're not going to ever make any money on that product. And they go, well, it's not worth it. It's just screw the beekeepers. Okay? We shot ourselves in the foot. So how can we get around this? And I've spent time, I'm in the currently involved with trying to do this in the United States. The New Zealand government came up with a brilliant idea. They said, you know what? These treatments, the FIFRA, the Federal Insecticide and Rodenticide Act, which is how we base all of our risk assessment on, is that you want to have no unreasonable risk to man or the environment. Man includes the consumer and the applicator. The environment is everybody else. With these chemicals, there is no risk to the environment. They're all natural chemicals that biodegrade rapidly. There's no risk to the consumer because all these are in our food. We eat them, every day, and very little risk to the applicator. As far as I'm concerned, and the New Zealanders said, wow, they should just fall outside of a regulation because there is no risk to man or the environment. So the wise New Zealanders granted an own use exemption to the beekeepers. And what it says is the exemption applies to a substance or compound prepared by a person for for use on animals or plants that they own, or any land, place, or water that they own or occupy. So that would be all of your bee locations. In a beekeeping context, the only exemption is commonly used when a beekeeper prepares and applies preparations containing generic substances, not formulated products. Generic substances you can buy off the shelf, such as oxalic acid or formic acid, and they're also allowing thiamol, to their own hives for the control of varroa mites. Right? So when I'm on the phone, on a Zoom conference with the EPA person in charge with this bill, I showed this, I read this to her, I said, what do you think? You can just absolve yourself of responsibility and liability by putting it on the beekeeper. It puts the whole onus of responsibility on the beekeeper. If one of your employees gets, swallowed acid or something, it's on you, it's not on the EPA. I said, this is just a win-win for everybody. And he said, can't do it. Okay, we need to have legislation passed by the legislator to do an own use exemption. So in New Zealand, they sell the kits. Here's the oxalic acid, here's the glycerin, here's the kit, here's the bucket to make it in. Totally legal as long as you don't sell it formulated. So this is what all the New Zealand beekeepers are using for mite control. So here is what I suggest, is that we beekeepers need to put a flame under our industry leaders and our regulators, our legislators, and say, help us. We're hurt. We can take care of our varroa problem ourselves. If you just give the freedom to figure out how best to use thiamol and oxalic acid and formic acid, let us take all the responsibilities. You don't have to worry about us hurting the man or the environment. Let's do it. So that is my final thought to you guys on that. Done. And sure enough, we put the strips in and here to keep the bees alive. And then those strips started to fail, and I tried Kumafos for 1 year. I go, oh my God, if this is about beekeeping bees, and I got to put, organophosphate with long residues in my beehive, I'm not interested in it. And so at that point, I stepped off the synthetic chemical side conveyor belt because I just thought it would just keep going. I thought that amateur apps would fail just as fast. It hasn't done that, but it is now failing now. So it was a hard learning curve, learning how to control varroa. Way back then, I had to follow most of the research from Europe because you guys are ahead of us on this. So Europe is ahead of us, then there's us, and Canada is about 2 years behind us, and New Zealand was about 10 years behind us, and Australia now is 30 years behind us. So when I go to New Zealand, it's like it's like deja vu. We don't even use those questions. You guys must have been on the internet. Because check the date of those posts. You don't have to repeat all of our mistakes again. So I thank the European beekeepers that most of the research I followed on varroa was from European, because you guys had it before us. And so then it's the learning curve for me to adapt those for the United States. And you guys keep these very different than we do. But that's more a function of the human influence than the bee influence. The bees are still influenced. They're still pretty much the same. So just because your beekeeping methods are different, it doesn't mean that your biology of your bees are different, or that the biology of varroa is different. It means that the beekeepers are different. So I'm not making any recommendations. I'm not suggesting that you change your methods, because what I said, I'm just showing you what works in my operation in California, what works in the United States, where I'm familiar with. I don't propose that I know anything about keeping with AC hives or beekeeping in Slovenia. So it's up to you to interpret what you see from me to apply to your own operations. One thing I tell people is, we got to help the beekeepers, we got to do this. I said, you don't got to do anything. Most businesses, 90% of businesses fail. Okay? It's not my job to keep everybody who wants to try to make money with bees to do it. You can't cure stupidity or anything like that. There's going to be a lot of people who start off, and it's going to be it. And in the US, I tell beekeepers, hey, you're all my competition. Every tip and trick I give you makes it harder for me to make money because you're going to be more successful. Okay, so that's the bottom line. So I'm not on a mission to make every beekeeper be successful in any way. Okay, for those who are interested in good, reliable information, I am happy to share that with you. Okay, so Understanding varroa, sustainable management, so like these rotating these organic treatments and eventually mite-resistant bees, that will be sustainable. This will be the most sustainable. This is stopgap until then. And then as the climate changes and we've been in this 20-year drought, worst drought in couple thousand years in California, we're 20 years into this, and it's just learning how to use colony nutrition and supplementing. How many of you in this audience feed artificial diet, pollen sub, or any kind of protein to the bees? Okay, just a few. So as your climate changes and there's less and less forage, and you get more beekeepers, you're already over carrying capacity, you may need to start feeding pollen sub. And I was starting out with bees. My first quite a few years as a hobbyist, I said, I will never feed sugar syrup to a beehive. I'm not going to feed pollen sub. That's unnatural. It's artificial. And then, after a number of years, a commercial beekeeper became a good friend of mine and said, Randy, I don't know whether sugar syrup is good or bad or this or that, but I can tell you one thing. You give a colony a gallon of sugar syrup at the right time, it's like waving a magic wand over that colony. It can really make them much healthier or survive. I realized, that is true. So I kind of got off that, I'm so natural bandwagon. He said, really what I care about is managing my livestock and keeping them healthy and productive. So I, for 25 years, I picked up all my beehives from when it dried up in first week of July and trucked them over the mountains up to an irrigated lucerne in the state of Nevada, where they did much better, and then there was a plant that bloomed in the fall that produced good pollen for wintering, and then I would haul them back. As varroa started to take its toll, it got harder to manage those bees when they're a few hours drive away. So we started experimenting with feeding pollen sub and learned how to keep bees healthy at home. So now, yes, we are feeding our bees a bit of artificial feeding in the late summer, but we're also home for dinner every night. And I like that. I don't have the carbon footprint of all that hauling of hives. So let's talk about using pollen sub. And I slipped together out of some much longer presentations, this one right here. So you can hand mix it. We also have mechanical mixers that we use for it, or you can buy it pre-packaged from the various manufacturers. You guys don't have small hive dealer yet. I didn't realize that coming here, so I put this in here. If you are feeding pollen sub, the bees will only consume it if it's placed within the cluster. Anything that hangs over the outside of the cluster, they're not going to touch it. And then that becomes a magnet for small hive beetle and breeding grounds. So if you're going to feed pollen sub, only put it in the middle of the cluster. Don't put it on the top of the hive. Put it between your two brood chambers, as close to the nurse bees as possible. The nurse bees do not respond. Okay, first thing to understand if you're a beekeeper, everybody knows that perfect frame. You pick it up, there's a band of honey to the side and across the top, then there's that nice arc of bee bread, and then there's a brood in the middle. When a forager bee comes back to the hive with a load of pollen, where does it preferentially on that comb place the pollen? Where? In that band around the brood, or where? Where's the forager preferentially place the pollen? On that frame. Here's the frame. Does it place it up in the honey? Does it place it in that band of bee bread? Or does it place it in the brood? So it places it preferentially right in the middle of the brood nest. And that pollen is then consumed very rapidly, often within an hour, by the nurse bees. That's where the main dynamics of incoming pollen are, right in the middle of the brood. Anything you see in that band, that's surplus. And that's what they don't need, the leftovers. And that's like that cupboard in your house with that canned food that you save for a rainy day. That's not stimulatory at all. You don't go in there because you want to eat that stuff. That's that sauerkraut that grandma gave you 10 years ago that you're storing for a bad day. That's how the nurse bees look at that band of bee bread. It's fermented pollen that they'll eat if they have to, but that does not stimulate brood rearing in any way. If you want to stimulate brood rearing, you got to put that pollen sub or just natural pollen as close to the center of the brood nest as you can. So there are advantages of using an unwrapped chunks rather than the papered chunks. What we do is we get both, or we make both, and we chop it up with a spade, we put a big chunk in, and we feed over 1 kilogram at a time. Okay, hungry colony will eat a lot. Many beekeepers underfeed pollen sub. That's just an appetizer, a small amount. You want to give a good-sized chunk. We press it down, and we want to squeeze between the frames, and it's right in proximity to the nurse bees, and it's very stimulatory to them fed that way. And the other question is, what do the bees do with it? And I didn't put the pictures in here, but we've done studies with a lot of studies with fluorescent tracer again. And what we found was they don't store any of it, the feedback. They consume it or they throw it away, but none of it gets stored if it's fed in this manner. Now, if you put dry granules of bee collected pollen in a hive, some of the bees will pick it up, actually put it on their legs. And then the funny thing is, if you're feeding it on top of the hive, so I put a rim on top of the hive, I put a piece of glass over it, and I put petri dishes of pollen sub and pollen to see what the bees would do with it. And when you initially put that powdery pollen in there, you'll see a bunch of bees come in there and get it on their bodies, comb it up, put it on their legs, and then you think they just walk down a couple inches to the nurse bees. If you crack that glass, they will fly out, turn around, fly down the entrance, come in the entrance, and then come back up. Because that's their behavior. They come in that way. So they will, if glass isn't cracked, they will go down, and then they will pack it into the cells, and then the nurse bees will eat it. But it's the nurse bees eating it in patty form, where it's moistened. They don't store any of that. So you can also dry feed pollen sub, and the foragers will just mob this. They will cover their bodies with it, comb it with their legs, and bring it back. They will store that in the colony. They will make beet bread out of it. The problem is it's really erratic, that out of one hive out of 10 will have every forager going to it, and the next hive won't have any foragers going to it. So it's very easy to do because the bees are colored with the pollen sub. So you can walk around your bee yard and look at the entrances, and you can see some hives with every bee coming back with pollen sub, and other hives with none getting. So what we have found, that's an easy way to feed, but it's very erratic. So we gave that up, and we actually put a measured patty in every hive. Because we want to create, we don't want to baby any particular hives. We want uniform hives, so that everybody's the same. Any that are not the same, we either combine them or get rid of them or something. We want to have all of our hives about the same for our management. And then generally, you're going to need to feed some either nectar or sugar syrup, because the nurse bees need a lot of water in order to create the jelly. So just feeding them protein, they also need a lot of water and some nectar or sugar syrup that apply for the sugars that they have to also feed to the larvae to mix with the jelly. So generally, you're going to feed 1 to 1, one part sugar to 1 part water for stimulation to get the nurse's sugar brood. You're going to feed 2 to 1, 2 parts sugar, 1 part water for fall feeding, or anytime you want them just to put on stores in the hive. Now, all the other livestock industries followed up on the work of those scientists who worked in the same time as the growth back in the 1950s. And every other animal industry got us way ahead of us as far as developing artificial diets. Almost any antibiotics, specific artificial diet for raising ostriches, or raising alligators, or raising weasels, whatever you want to raise. And not only that, if you're raising chickens or cattle, you will have one artificial diet for their first week of life, and then another one for the next 2 weeks of life, and another one for the next month. And they change the ratios of the amino acids throughout those, and maybe the vitamins and the minerals, because these nutritional needs, when you're growing bone, you need more calcium. Once you've grown that bone, now you're going to need more protein for muscle mass, Then you grow hair, so you need a different amino acids to grow the hair. So we haven't developed that far. We are so far behind on honeybees. So the question always is, there's a bunch of people selling pollen subs, and everyone they claim to be the best, okay? So the problem is, we don't have, you know what the magazine Consumer Reports is? Okay, in the US, there's a magazine, it's nonprofit, and if you want to find out what the best toaster is, or the best, best frozen food is, they buy at their own expense, through their subscribers, all these products off the market, and they run controlled tests, and they compare them, and then they report the results. We don't have a Consumer Reports for honeybees. We don't have independent testing. If you're raising roses, they have the All-America selection. So if you come up with a new cultivar of rose every year, they have a whole bunch of volunteers and they plant a bunch of different cultivars in different climates, and then they test them all, report back and say which ones perform best. That's the All-America rose selection. They have it for other plants too. We don't have that kind of independent testing for honeybees. It's really unfortunate. So, yeah, me. So I do a lot of independent testing of products that come onto the market, including the probiotics. I've got a bunch of data on that too. And I agree with Ivana that most of them on the market are, I'm going to be publishing a whole bunch of data with next-gen sequencing where we really follow that we treated them with antibiotics, look for recovery, look for build-up, weight gain, look for quality strength, look for pathogens, but decrease the pathogens. They did nothing because they didn't use the species of bacteria that actually will colonize the bee gut. So you can't use an animal probiotic, it doesn't do any good. Now, not to say that there couldn't be any probiotics. There could very well be, if they did the next generation and actually cultured the specific strains of bacteria that live in the bee gut, so it could work. Anyway, so every manufacturer says, well, ours is the best, but they don't show much data. So I have, over the years, run a number of trials to compare them. 2013, I ran one testing most all the pollen subs that were on the market with a negative control of just sugar, equine sugar alone, and then patties made of natural pollen right here. And then all the tested subs fell between the natural pollen and the negative control. And the negative controls typically, you can see, they go from 5 grams of bees down to 2 and almost nothing. They won't make it to the winter. So I intentionally put them in the worst yards where there's no natural pollen coming in. So that was 2013. We found that some of the top tier subs actually performed very well. But one of the problems is when I analyzed this, I found out, well, that's because they had a higher protein content than these right here. So in my subsequent trials, I then matched them for protein content to see. And so I've run other trials I'm not going to show you. I'm going to jump ahead to my big trial in 2020. And the reason is that this is what California Central Valley looks like right now. The almonds are in bloom right now. And what you have is let me see if I have it. No, I didn't put it. If you notice, each row of trees is a different color of flower. So they plant different cultivars. They're all self-infertile. They can't pollinate. They're all clones in a row. So they cannot, one tree in that row cannot pollinate another tree. You have to have bees carry the pollen from one row to the other. And the growers pay us a lot. I started out almond pollination getting paid $10 a colony to win. We're making $225 a colony. Now, in the years that I've been doing this, the price has gone from $10 to $225. That changes everything. And the growers grade our colonies for strength. We get paid by how strong they are. So producing strong colonies by February is really important to us. And first thing, a strong colony requires a good cluster going there. This cluster would probably be too small to make top grade. If this were a fall cluster, that would be too small. That would be really big going in. Because in January, when it starts filling up, the queen's egg laying is limited by how many combs are covered with bees to give them more cells to lay the eggs in. So you have to have a large cluster to start with. So that means we need to get pollen subs in the fall to get a large, well-nourished cluster of bees going into the winter. And this is what our environment looks like all from July on. There's nothing for the bees to eat, and there's no fall bloom. So we feed pollen sub. We control varroa first in August. And then once we have the mites down to 0, so you don't have viruses, then you start rearing more the bees of your winter cluster. There's no reason to initiate brood rearing if you have a high mite level, because you're just making more mite food. So first eliminate the mites, and then start feeding pollen sub in the fall. Now, if you're a hobby beekeeper, and your main concern is swarming, you don't want to feed pollen sub in the fall, because you don't want a great big cluster, because otherwise, February, you're going to have pollen swarming. So you have to look at what your goal is. If, on the other hand, you want to sell a whole bunch of nucleus colonies in the spring, then you want a big cluster going in there. You want to grow them up so you can have bees to split or sell come springtime. So just because we do this, and we do both of those, we pollinate almonds and then we sell 1,000 nucleus colonies, okay? So if you're the hobbyist and your main concern is just having some bees and not having them swarm, then you may not want to keep almond subs. So when we take our bees down to the almonds, then what the growers want to make sure you actually are going to come through on your contract. They say, can you get the bees down here? We go, we're on a pollen and nectar flow up here in the foothills right now. They're doing great. You want us to bring them down now to the desert? That's what, it's a desert for bees. There's nothing for the bees to eat. So we'll bring them down and then we'll put 1.5 kilos of pollen stuff on them because they're already rearing brood based on natural pollen. But we want them to continue that brood rearing until the almond trees start blooming. So those are my two sons doing that. And we are facing more droughts right here. So if you look at drought intensity, the more intense the drought, the more red and purple it is. This is averages from 1950 to 59. You don't see it very much there. Averages from 2000, 2009, we're starting to see droughts. Okay, so where are you guys at right around here? Look at expected for 2060 to 2069. Some of you guys are still going to be around here. It's not looking good for you. No. You know this. You know this, okay. So that means you may want to learn about supplemental feeding. So in 2020, I want to answer this question. Anytime you do a research project, specify the question that you want to answer. And on this one, do some pollen subs, and you can't say are they good, what metric? So our metric is to promote colony growth to get how many frames of bees that I get paid. We get paid $25 per ton of bees going to almonds. So a very simple metric, dollars into my pocket. How many $25 payments do we get by feeding one pollen sub rather than another? Okay, so this is from the 2013. By 2020, we had 2 new ones on the market, and some commercial beekeepers had developed a homebrew formulation that they liked and said, Randy, we're curious how our homebrew formulation, which we can make very cheaply and looks really good to us, how would that compare to the products in the market? And they gave me some money to help fund this program. I had some of the pollen, one of the pollen stuff developers say, hey, Randy, they are $50,000. Can you test my product? I said, well, I'll test your product all right, but it's not going to be on your money. Okay, I want the beekeepers to pay for it so that we see. So, so this is the boat saw patty made by Man Lake, which we have used for quite a few years and works pretty well. Although this year, when we tested it, they changed the yeast and the bees hated it. So it wasn't a fair test. After I ran this, they changed back to the other yeast, so it actually works better. So this actually worked worse in this year than we expected. Another company makes a very common patty, and we got the one with the 15% natural pollen in it. Data makes, this is their new one, artificial pollen 23 is what they call it. And developed by a nutritionist who I've corresponded with quite a bit. He's helped me out too. Then a sugar patty, a fondant we made to match roughly the amount of sugar in these, but no protein in it at all. Mega Bee developed by Gordy Wardell from USDA many years ago. Ultra Bee, Man Lake's flagship, which is very similar to this, but in patty form and a little more expensive. And then the homebrew with 20% natural pollen from the commercial beekeepers. And then this new one with spirulina algae in it. But these guys also tried to control varroa and added a bunch of thyme oil, which the bees hated. So it performed very, very poorly in the trial. After this trial, they switched and they took the thyme oil out of it. So if you have small hybrid, the thyme oil thinks the small hybrid doesn't like it. But if you want your bees to eat it, you take the thyme oil out. Here's my son Eric. We ran this trial with 144 hives. 18 hives per each of the patty types. We replicated in 3 separate yards to see we got different results per yard. It's always good to replicate any trial of honeybees, either in different years or in different yards, to see if you get the same result. And in one trial, one time in 1 yard, you can't count that that's going to be consistent. Now, this is confusing. We had to make a bunch of feedings with all these, how many types? There were seven different types, plus the sugar, so 8 altogether in sugar control, and not make any mistakes. We couldn't feed the wrong one. So every day we went to feed, we would count out in color-coded tubs, 18 patties, and we put a color code on each hive. We didn't care, we didn't pay attention to which was which. We couldn't blind ourselves completely, but we didn't pay attention to it. And then we'd lay out the patties on top of every hive, and then a quality control person would walk around, double check to make sure they were all laid out properly, and then we would crack the hives and put them in. We chose yards, this is my 2 sons, that we knew the bees were going to crash it, that there was just nothing for them to eat from our experience, okay? And we fed continually pollen seven syrup from late summer into winter and cut up. So we started feeding in August, took our first grading of them, fed pollen syrup and seven syrup. So pollen syrup feedings are the yellow boxes. Feedings of syrup are the round circles. And we've got this unexpected yellow star thistle, so Centaurea, and you guys may have this around here. It gets 10 days to produce pollen and nectar. We weren't expecting that. So we did not feed pollen sub, and that was in only 2 of the yards. So we skipped those 2 yards then. Then no feeding, we graded midpoint November, stopped feeding. So this is all birth period. And then starting middle of December, we started feeding again. And then we had a natural flow from almost alder trees. So once that started coming in, we had 21 days before it affected emerging bees. It had affected pollination. So 21 days after the alder flow started, we did our final grading before going to almonds. So this is typical of what the combs look like in mid-October, just before going into the winter cluster. Only from artificial feeding, but notice there is no stored bee bread, because there was no natural pollen coming in. The only nutrition they were getting was strictly from the artificial diets being fed to them. And then we did our November midpoint grading with my newest technician, who was Eric's son, my grandson, who was out of school due to COVID, and boy, he was sharp for a quality control recorder, and he made sure we got everyone right with our right color and get the numbers down there. So we picked the boxes up, we pick up both, split them apart, grade from the bottom of the bottom box and then from the top box, and very accurately grade for strength. Okay, so this is that midpoint grading. This is the November cluster size for frames of bees. Now, it was a cold day, so the clusters were shrunk, and they were pretty small. Now, I'll tell you right now, we had this extremely hot, dry summer. Most of the colonies shrunk in size. They were smaller. The August grading in hot weather, the clusters were larger, but when we graded in November, it was cold, so they were small. So, but it doesn't make any difference because we were grading relative to each other. Okay, so we don't go by the absolute value, we go by the relative comparison in strength. So this is our colony strengths of the different color-coded patties. Now take a look at the red one, which was the global, and the home group, because they were exceptional there. The other thing to look at the error bars. Look how consistent. There were 18 colonies in each group. 18 hives, and look at how small the error bars are here. When you have small error bars on every group, that means that data is probably pretty good because you're so consistent on the small error bars there. So we went into winter like this. Now, what's interesting, I often collaborate with university or UC, Agriculture Service, USDA researchers who have the equipment. So I sought one out and said, hey, can you pay for the pollen seven chemical analysis? Can you also then look at bee weight, dry bee weight, and can you also then do next-gen sequencing on the gut microbiome? Okay. Okay, so I did all the theory work. He did the lab analysis. So here is, on the left column, that is the total frames of bees in the group for all 18 hives. The right that's the right column. The left column is your head and thorax mass. Okay, so that includes the hypopharyngeal glands and the flight muscles. Okay, look how closely they correlate. So what this tells you is that difference was due to the colonies getting greater nutrition, and you got heavier bees, more body mass with the better nutrition, and that also then meant you had more frames of bees. So total number of bees in a hive correlated to how well fed they were and how large they were. So now you might wonder, well, what variables are there in these pollen subs? So let's look at the protein content. They vary from 22% down to less than 15, and there's no correlation between protein content and performance. Keep looking back at the two starters. Fat content. Two of the lowest fat contents were the best performing. Okay? And by the way, the critical sterol, which is in the fats 24-methylene cholesterol, when I had this one right here was 0. Okay? So even though it lacked that one, the bees were able to synthesize their own and do okay. Sugar content. We analyzed the sucrose, glucose, fructose, and total sugars would be the solid color right here. Nothing special about sugar content, okay? Relative prevalence of the core gut bacteria. So the height of this is total number of bacteria, and the different colors are your core groups. So you can look at the relative percentages of them, and the species composition was the same, whether they were fed pollen or not. But some of them had more. So let's look here. That one was 20% pollen, that was 15% pollen. No correlation to the amount of natural pollen. You guys get an idea of how fun bee research is? Everything you think is going to be make sense to you? Yeah, throw that away. And then, since I had some of my resistant breeders, potential breeders that we did not treat, we treated all the rest of the oxalic acid, I said, well, let's take a look and see if oxalic acid made a difference in the gut microbiome. That's good data, didn't make any difference. So, the answer to which variables correlate with performance, we have no idea. We threw everything out the window. It's got to be something else. So, in December, we resume feeding again, and again, no natural pollen. This is all based upon the initial feedings of these overwintered colonies, with artificial diet again. We did our final grading on a very, very cold morning on February 1st, just above freezing, with very tight clusters. Final results. So this line, this is your endpoint strength, frames of bees for each colony, and this is your midpoint strength, okay? So this is showing growth from the winter cluster up to final grading. This would mean no change in strength right here. So if they're above this line, that means they grew. If they're below this line, that means they shrunk. Look at the colors. Do you see a pattern? No. Which color is more prevalent above the line? The homegrown one, yeah, and the blue. The blue one and the homegrown. Which ones are more prevalent below the line? Yeah. The healthy bee and the native control, lots of white, lots of green. So we're already seeing a big difference in growth right there. Now, was it consistent from yard to yard? Yeah, it was. All the yards were pretty much the same. The colony started out averaging 8.5 frames of bees in August. They averaged out down weaker in November during that cold cluster, and then some grew, and the native sugar controls continued to shrink in size. They not only did not grow, they continued to shrink. Did it have to do with pollen? Well, these two did have pollen, but this one had 0 pollen at all, and performed almost as well. And the thing was, this was our favorite bulk soft when they switched the yeast in. If they had switched the yeast, my guess is that this one would have been right after the two of them with no pollen. So my take home is, I don't see that any natural pollen is necessary in any way in an artificial diet. We'll get to it in a minute why. Now, how about colony loss? So this is percent of colony losses. Didn't lose any colonies in global. We lost 30% with the sugar control. Okay? Now, just for a histogram of comparison, if you're going to compare, I'm not going to give you a bunch of numbers for statistics. Your eyes are as good as any statistical analysis. You look at the histogram, the distribution of 2 different groups. So this means out of those 18 hives, these columns will add up to 18 for each group. It shows, on average, the sugar control colonies average 2.7, median of 2.9 frames a beat. Very, very weak. The homebrew, both the mean and median were 8.3 frames. If you look at these two groups of hives, you can see, you know these statistics. There was a big difference based upon pollen sub type. All statistics does is just come up with a probability value that researchers spend days trying to tease out a p-value of less than 0.05 for probability. But this you can see very strong, very low probability. Okay, final analysis. I said, well, easiest thing to do is out of those 18 hives, how many total frames of bees were there that would pay me $25? And the home group. We made good money on the home group. 3.5 times as many frames of bees in the home group as there were in the sugar controls. So very clear difference of what you're looking at. Now, step the question. Why did some subs perform better than others? Now we start the deep dive. You all go, oh no, not again. So we get to the concept called Liebig's barrel. And Liebig's barrel says any living organism, whether it's a plant or an animal, requires a balance of nutrients for optimal growth. And he says, imagine that all the nutrients were in balance, and each stage of the barrel represents one nutrient. One may be carbohydrates, one may be iron, one may be zinc, one may be the amino acid tryptophan, one may be vitamin C. If any nutrient is out of balance, deficient, that's called the limiting nutrient, and that stage of the barrel is lower, and that determines maximum growth. Doesn't make any difference how high the other stages are. Your growth is limited by the first limiting nutrient. Okay? And that's where we're going to go from now on. Figure out what the limiting nutrient was in these pollen subs that prevented them all from growing optimally. For example, I noticed you guys got dandelions blooming already. We don't have dandelions blooming yet. You guys are having a very early spring. Now, bees love dandelions. If you put these out on just solid yellow dandelion flowers, what will happen is all those colonies will bloom and die. Because dandelions are missing short on 2 essential amino acids and not enough to sustain growth of the colony. So on dandelion pollen alone, colonies will wither away and they'll die. Same with pollen stuff. If you have a limiting essential amino acid, you're going to wither away and die. The state of our knowledge of pollen subs for honeybees was published in the Netherlands by Antonius de Groot in 1953. I was 2 years old. Okay? And everything we know is based upon this graph right here. This one single graph. And the numbers that we have for the growth recommendation are based upon the inflection point of these curves. See how the inflection point? What that means, he fed these adult bees in cages, an artificial diet made solely of essential amino acids, and at either 1% concentration, 2%, 3%, 4%. So if it was deficient in it, that means if you add it, it will increase the amount of weight gain here. Once you reach the ideal amount, there's no added benefit to adding any more. So you compare, this one would have a value of 4%, this one would have a value of 2%, this one would have a value of 4.5%. And tryptophan just happened to come out at a value of 1%. And for that and other reasons, the growth said, oh, I'll just normalize the tryptophan because it got a value of 1. Everything else would be some multiple of tryptophan. So he came up with this whole 8-page paper was all about ratios until figure 15. And he made the terrible mistake of saying percentages. And he should never have done that. Because that's the only one anybody pays attention to. And so they all published, the black line would be the minimum percent in a diet that the growth recommended. But they don't read the rest what he said. He said, this is not for optimal growth. This is for absolute minimum growth, much less than you would get on natural pollen. And when we analyze these diets for all these 10 essential amino acids, they all were above the growth's recommended value for minimal growth. So all the manufacturers said, yes, these are complete diets. They're really good. And I took this as a, wait a minute. We have an abundance of leucine. All that leucine would be going to waste. So how important is leucine? Well, back to the growth again. It's the predominant, most important essential amino acid, more than anybody else. And the growth's error, and I have no criticism of any of yours. It's very clear that it needs to be interpreted, is that he normalized the leucine and has led us astray for 70 years here. If he had normalized the leucine, it would be much more informative. So, how important is leucine? What he did, he fed newly emerged adult bees, took their weight, either their increase in dry weight or their increase in nitrogen content, at 7 days and 14 days, with deficiencies in these amino acids. And if it's really critical, that deficiency will show that they will stop growing. And which one comes through? Leucine. Boy, they'll grow for a little bit for 7 days, and then if they don't have enough leucine, man, they start losing weight. These other essential amino acids, they'll just keep growing despite not having that amino acid. So really, we need to focus on these few right here: leucine, threonine, valine, and maybe histidine right there. These are the critical ones that you do not want to run short on. You guys all still with me? Yep. Okay. I'm trying to slow it down for because the translators are getting tired. And I talk fast and burst them out. Now, let's do the same graph again. This time, instead of normalized and let's normalize to leucine. And look at the deficiencies. Valine, that critical amino acid, way deficient. Threonine, deficient. Histidine, deficient. Go back here. We got valine, threonine, and histidine. They're critical ones, and they're all deficient on those critical ones. Oh God, I get goosebumps right now. Because when I did this graph, all of a sudden I go, wow, eureka. I just figured something out right here. Everybody's been using the wrong normalization to figure out the optimal diet for honeybees. So I created that amino acid calculator so that we can compare the diets. The gross recommendation are the gray bars, and the green are the formulated diet. So I did one for royal jelly, and again, look how closely the royal jelly matches the growth. A little bit low in isoleucine. Royal jelly is a little higher in lysine. So the growth organizations were really deficient in lysine for nurse bee growth. And then look at a mixture of known nutritious natural pollens. Matches the growth ratios almost perfectly. So now let's look at all these artificial diets. And what I did is I ranked these from the best performing down to the poorest performing and down here with any minor deficiencies with a small circle and major deficiencies with a large circle. You notice the pattern? The more deficiencies there were. This is all published. It's on my website. Not that you just. The more deficiencies, the poorer the growth. So I said, let's see if we can plot a correlation. Here's our correlation. So this is the ending frames of bees per treatment, and this is this. I found that the summing up the deficiencies gave me the best result. And relative to leucine, and look what you do. An R squared of 0.85. That means 85% of the variation can be explained by this variable that I came up with. And healthy bee, if it had that time mode, would have probably been right on the line, also right there. We would have got even a higher R squared. When you see it with a field trial with honeybees, an R squared of 0.85, usually you're really happy with an R squared of 0.6 or 0.5, okay? 0.85, and then a probability of 1 chance out of 2,000. Okay, very, very low probability of this being by chance. So it really shows it was that. So then I went further research and I looked at everything I could find published on the needs of the nurse bees and the larvae, and I came up with my own recommendation higher in lysine to compare to. And that's so you have these both on my calculator to try to figure out your own. And so I already showed you how to use this right here. I've got common ingredients here, and then you can add the analysis. So if you're living in Saudi Arabia and what you have is ground date kernels as a protein source, you can put that in there. If you're living somewhere else where all you have is peanuts, you can put that in there. So beekeeper, I made this for beekeepers anywhere on the planet to look at their available protein sources, put the analyses in there, and then they can play around and try to come up with a perfect pollen sum. Anyway, preliminary research, again, we need more files to confirm this. And I'm, again, collaborating with USDA and I got some different kind of stimulants at home, so hoping that this summer we'll get back onto pollen stuff again, because I gave each of those manufacturers how to perfect for just very low cost, adding a few essential amino acids, and I don't know that any of them have done it. So one of them will probably, I already talked with their people, so I can probably elaborate within the summer, do another trial, balancing. I'm going to do a diet with no pollen at all, and that's what pollen seeds, and I get it to perform well. Oh, you don't need that. Oh, that was about the, okay, that's it.